Okay, so let us continue with linear delay model. Just a quick look at what we have been doing so far. New delay model, the last delay model for this unit, also called as the linear delay model, and equation is delay d equal to g into h plus p, and this is a delay which is in terms of tau, and tau is the 3RC delay for some particular technology. And because we are in terms of tau, we don't have to worry about the technology. This will stay the same for any technology, so the design can be reused. And in terms of the G, H and P, we already discussed all those terms. G is called as the logical effort, which is in some ways the cost of a gate in terms of its delay. H is fan out, or also defined as the output capacitance divided by the input capacitance, and P is a another component called as the parasitic delay, which is related to the diffusion capacitances. And we also mentioned that equation is similar to equation for potential energy, mg into h. Mg is the cost, which is measured in terms of the weight of the body, and h is the height. Similarly, here also g is the cost of the gate, and if it has to drive h amounts of fan out, then cost becomes g into h. Added to that is a constant parasitic term p. So total delay is gh plus p, and we looked at all these terms. We calculated it for many different gates. All is done. Now we need to extend it to the method of logical effort, and we will do that and come up with what is called as the method of logical effort when we have to calculate this for a series of gates. So in most digital circuits there will never be one gate. I mean, that's just a toy example that we can look at for calculating logical effort G. But generally, any circuit will be a series of gates, which is also called as a path, which is what we have in the blue line. And we will be given the input capacitance and output capacitance, because whenever a designer is responsible for a block, he has to get the input capacitance from whichever signal has been given to him from another block. So the input capacitance in this example 10, that will be known, and the output capacitance, he has to give his signal to another block, so that person will be expecting the capacitance. For him it is input capacitance, for us it is the output capacitance, so that number also has to be fixed beforehand. So this 20 and 10, these two are fixed beforehand, and once the functionality is known, we use logic optimization, etc., to come up with the best possible series of gates between the input and the output. That is our path. So what all things are fixed in this path? The input capacitance 10 is fixed, output capacitance 20 is fixed, and these gates which form the logic, or which are responsible for realizing functionality, those are also fixed. Given these things, okay, how can we, now here is the important question, how can we size the gates, right, individual gates, such that the delay for this particular path is minimum? This is the question, and this is where the method of logical effort, or the linear delay model, has a clear advantage over the first two delay models. So we have three delay models that we know so far: RC delay model, Elmore delay model, and the linear delay model. RC delay model is the simplest. Suppose somebody just throws a circuit at you, you can quickly say what is the delay by calculating the RC delay model. Elmore delay model, it's also simple, but generally it is used by tools for calculating the delay for large clock networks relatively quickly. You don't have to do simulation. So that is the functionality of those two delay networks. Now, the linear delay model, it's a new delay model where we have extra functionality. That is, it is not just an equation to calculate the delay. We can do that also, D equal to GH plus P. But in addition to that, we are also going to see how to use it to size these gates. So for example, here X, Y, Z are not known. Okay, they are variable. What values should I put for X, Y, Z such that the delay along this blue path is minimum? And that is what the method of logical effort gives us. It gives us a very simple method based on a inequality. What can we put for XYZ? No trial and error. Okay, trial and error is problematic because this is a very simple circuit, and if the options are more, then you have more work to do in terms of trying more and more things. But here we are given one certain set of numbers, and that's supposed to be the best possible set of numbers. You cannot do any better than that, and that is what the method of logical effort gives us. Okay, so before we go into the method, let's just see what is the definition of a path, etc. So we have logical effort. Now we are slightly extending that definition to the logical effort of a path. Okay, from logical effort. Okay, so it's very simple, just extend it directly. Okay, we have a series of gates, for example, here, and what we know is this number G1, G2, G3, G4. And remember what we discussed, the X, Y, Z, the size of the gate, don't determine the value of the logical effort. They can be anything. If it is a two input NOR gate, the logical effort G2 is always 5 by 3. That is why we can write this number without knowing X. And that is one of the advantages of the way we have defined it also. If I have to know X to calculate the logical effort, then it's impossible to use this method at all. Okay. So for that reason, here also two input NAND gate, I don't care about this Y. The logical effort is 4 byte. Similarly, inverter, I don't care about the Z. Logical effort is 1. So if I have these things, what is the logical effort of the path? Okay. So we can define that by having this equation. Instead of small g, now we have capital G, which is defined as the path logical effort, and that is going to be the product. Very important to remember. Okay, not the sum. Okay, it is a product. And if you want to imagine it in terms of multiple gates, it is one gate driving another gate. So if you bunch both of these, it's like two functions. Composition of two functions is f into g. Similarly, if you have two gates, one gate is driving the other gate, so together if I want to combine them into one gate, what is the cost of that gate, or what is the logical effort? It is the product of both the logical efforts. That is what this equation is telling. Capital G is product of individual GIs. Okay, and similarly, we can go from single gate to multiple this thing. Okay, F equal to GH for small single gate, F equal to capital F equal to product of the individual GH, which is given by GIH, product of. Okay, and similar to capital G, we can also define capital H. It is just output by input. So once again, going back to the previous diagram, here if you calculate H for each stage, that is H1 is x by 10, H2 is y by x. So if I want to calculate H1 into H3 into H4 into H5, H1 into H2 into H3 into H4, x by 10 into y by x. So the x and the x will get cancelled. Okay. Similarly, when I do h2 into h3, the y and the y will get cancelled, and h3 into h4, z and z will get cancelled. So if you multiply h1, h2, h3, h4, you will only get output capacitance. Okay. So that is a simplified version. We can just write capital H as the final output capacitance divided by the first input capacitance. So for example, in this case, capital H we can directly write as 20 by 10. we don't have to know X, Y, Z, because as we just saw, they will all get cancelled. So this product, that is the capital F, we can write for any path without knowing the individual sizes. Okay, because we know the small g for every gate. Once the gate is set, I know the logical effort. Similarly, output capacitance, input capacitance will be known because that has to be decided beforehand. So this whole thing, that is capital F, okay, for any path will be known beforehand. That is the first thing. Now, for example, here in the previous case, we can calculate it. It's very simple. Capital H. Okay, let's say I want to calculate the logical effort of the path. Okay, so capital F equal to GH equal to G1 into G2 into G3 into G4 into H equal to G1 is 1 into G2 is 5 by 3 into 4 by 3 into 1, okay, because it's an inverter, into 20 by 10. So it is equal to 20 by 9 into 2 equal to 40 by 9. So this is the path effort for the example. Okay, so this path, the effort is capital F equal to 40 by 9. So this we know, right? So now is the question, important question. How? We will come back to this in a second. Okay, how can we determine, okay, what is the best value for XYZ? So in this example, this 40 by 9 is fixed. We cannot change it because it is a product of two things. One is G1, G2, G3, G4, which is the gates. Like we said, that comes from the design. The logic optimizer will do whatever it can and give us the best possible set of gates. So we cannot change that functionality. Similarly, capital H also is a fixed number. We fix it before the design begins, and because of which this number is a constant, 40 by 9. Given this 40 by 9, what flexibility we have is we can choose values for these x, y, z, okay, such that the total delay is minimum. Now we also need to look at one particular thing. We have capital F, right? Let's type that here. Okay. What you have here, capital F, is not the delay. Okay, it is a completely different term. It is called as the effort of the path, GH, and of course we have to add the P also. But given this path, what is the delay of this path? The delay of this path is another term which is given by, okay, so this is the delay of the path. That is, we have four gates for this path. Each term is going to have some GIHI, okay, and each term is going to have some P. If you add all of those, add, this is important, this is not product, okay, delay is the sum of the individual block delays. This will give us the delay for the whole path. So what we have to do now is, given this fixed number 40 by 9, how do we choose x, y, z, okay, to minimize this bottom term? That is, the sum has to be minimized, and for that we have a simple equation, okay, which is also called as the arithmetic geometric inequality, AMGM inequality. It says that there are two types of means. One is the arithmetic mean and one is the geometric mean. Arithmetic mean is what we always call as the mean. We generally use it by default as the mean. The geometric mean is another type of mean, where instead of summing, we will product all the terms in the list and take the nth root. So that is called as the geometric mean. And the inequality states that the arithmetic mean is always greater than the geometric mean, and only in one case we have equality, that is if all the terms in the series are the same, and in that case the arithmetic mean is equal. That is the lowest possible value for the arithmetic mean. Any other numbers you put, arithmetic mean will be greater than the geometric. This is the inequality, sorry. So now let us come back to our this thing and see where all these arithmetic mean, geometric mean and all are coming into the picture. Okay, so the geometric mean is nothing but capital F equal to G into H product. Okay, geometric mean, suppose I have five numbers, say 5, 6, 7. What is its geometric mean? It is nothing but 5, 6, 7 to the cube root. Okay, now arithmetic mean is also nth root of GH, not just GH but nth root of GH. Arithmetic mean is sum by n. So this is nothing but delay. Okay, this is the first thing that we have to realize. What is the geometric mean? That is the capital F. What is the arithmetic mean? That is somewhat related to the delay. So when will delay be? This is the inequality telling us that if I want to minimize the delay, that is our objective, isn't it? We have a delay for the circuit. We want to minimize the delay. How can I choose the XYZ to minimize the delay? And what the arithmetic mean, geometric mean inequality tells us, if you want the minimum value for the arithmetic mean, okay, you can get that by choosing the values to be same for all the blocks. Okay, and what should that value be? That is also very simple, equal to, okay, GH to power 1 by n. That is, I have the GH fixed 40 by 9 in that case. Now in that case the number of stages was 4, so n equal to number of stages. And if I satisfy this particular inequality, that is for every stage I'm going to put the value GH to power 1 by n, then I am going to get the least possible delay. That is the very simple outcome of the arithmetic geometric mean inequality. So for example, G equal to 40 by 9 only we will take, equal to how much? 40 by 9 around 4.44. Now I have to put four numbers for the terms such that their products are 40 by 4. I can choose anything. So for example, 1, comma 1, comma 1, comma 4.444. Okay. So if I choose this, then I am getting the product that I require, because 1 into 1 into 1 into 4.44 is 40 by 9. But now the delay equal to 1 plus 1 plus 1 plus 4.44 equal to 7.444. This is one number. Okay. So is this the minimum? Not sure. Let us try another combination, which is 2.22 comma 2 comma 1 comma 1. Okay. This also gives me the required G. Now what is the delay? Just add up those. 2.22 plus 2 is 4.22 plus 1 plus 1. So about 6.22. So we have done better, right? Now, is this the best possible? What is the best possible delay? This is the trial and error method. We can keep going on and on, but we don't want to do that. Best possible delay is 4.44, okay, to power 1 by 4. That is the fourth root of 4.44. How much is that? 1.45. And now delay, multiply that by 4, you will get around 5.80. And this is better than 6.22 and 7.44. You can try more and more and more numbers, but this inequality will automatically give you in the first try the best possible combination. So for our case, how much should we put for each block? How much should we put as the GH product? That is 1.45. If we put this, we will get the minimum possible delay of 5.80. And this is what the arithmetic mean geometric mean inequality gives us. We don't need to do the trial and error part. Directly in the first shot itself, it gives us the best possible options. And if we put that, we are assured that the delay will be minimum. Okay. And that is what we have here also. We have n stages. Okay, this product is f. The delay is the sum of each stage delay. Okay, and this is the f to power 1 by n. That is the minimum value that we are forced to set for each stage. That is for each stage g1 h1 product, okay, should be equal to f to power 1 by n. And once we set this, okay, the small mistake here, this should be capital N for the number of stages, or sorry, small n is fine, n into f to power 1 by n. This is the GI-HI product sum. That is, if I have 4 stages, for example, it will be 4 into GI-HI to power 1 by n, what we saw in the previous example. Okay, that will be the sum, and this will be the sum of the parasitic delays, sum of individual stage pi. So if you want, I can write it again here. Okay, this is the total delay, and this is what we have to calculate as the delay for the full path, and this number is going to be minimum if we use the method of logical effort. Now let us go back to the example, okay, and try to find the values for x, y, and z. So what we know already we will write, okay, that is f to power 1 by 4 equal to 1.45. In fact, even one line before that we have calculated, we know f equal to 40 by 9. So f to power 1 by 4 equal to 1.45. Therefore, to minimize delay, we set GIHI equal to 1.45. Okay, this means G1H1 equal to G2H2 equal to G3H3 equal to G4H4 equal to 1.45. Okay, to calculate sizes of individual gates I, X, Y, Z. Okay, start from the first or last, doesn't matter. Okay, let's say we start from the first stage. So G1 H1 equal to 1.45. Okay, so therefore, 1.45 What is the value of G1? It is 1. 1 into H1. Now what is the value of H1 for the first stage? Output capacitance divided by input capacitance. Output capacitance is how much? That is X. Input capacitance is 10. So X divided by 10. And this is the equation that will let us solve for X. What is the value of X? X equal to 10 into 1.45 or 14.5. Okay, so let's go to the next state. G2H2 equal to, how much should it be equal? This number we already know. Method of logical effort, every stage GIHI equal to 1.45. Therefore, G2H2 also equal to 1.45, which means, okay, now what is the value of G2? It is a 2 input NOR gate. So G2 is 5 by 3. 5 by 3 into, okay, H2, output by input. Output is Y, that is this value. Input is X, which we just calculated as 14.5. So Y divided by 14.5 equal to 1.45. Then solve for Y. Y equal to 14.5 into 1.45 divided by 5 by 3. So 12.61. Now G3H3 equal to also 1.45, which means that what is the value of G3? 4 by 3. 4 by 3 into Z divided by Y, which is 12.61, equal to 1.45, which means Z equal to, solve from this equation, 12.61 into 1.45 divided by 4 by 3, 6.525. Now finally the last stage. Now here we can see something interesting. This is also 1.45, right here, but we know Z, we know output capacitance, we know input capacitance. There's nothing to calculate. But here what we can do is we can do a check. If the calculations we did were correct, then automatically G4H4 using the Z that we already know, it should give us the same value 1.45. Okay, so let us check that. G4H4 equal to 1.45 question mark. That is, we are going to check if it is equal to 1.45. G4 we know is how much? 1. Okay, into H4. So H4 is output capacitance by input capacitance. Output capacitance is 20. Input capacitance is, let's check that. This comes to around 3.06. So something is wrong. So we have done something wrong in our calculations. So we have to go back and check the calculation. So let us, okay, so sorry about that. So there's a small error that we did here. This comes to around double of that. So 13.7 or something. So if we use that, remove this again, 13.7, we will get 1.45 automatically for G4H4. So that check tells us that something was not right. So we have to start back from the first, and in this case the Z value was not correct. So now we get the correct value of Z, which is 13.7, using which G4H4 we can verify That is, we don't have to calculate anything, but we can verify it's still coming up to 1.45, and it does come up to 1.45. And finally, we can calculate the delay equal to 4 times 1.45. This is the term n into f to power 1 by n. N in this case is 4, f to power 1 by n is 1.45. 4 into 1.45 plus, okay, summation of pi. What is the parasitic delay for each case? This is a inverter 1, 2, 2, 1. So 1, 2, 2, 1 equal to 5.8 plus 6 equal to 11.8. Now, this is the delay for our logic path, and this is the best possible delay. You cannot do any better for any other values of xyz. Okay. Now, this is the method of logical effort, and this is almost 75% of the method. One small addition we need, which I skipped over before, but we need that also. That is when there is what is called as a branching in the path. So for example, here we see that it's going along two directions. Okay, and whenever it is going along these two directions, this is one path, this is one path, and this particular node is where a branching happens. So this branching is going to create a little bit of a problem if you don't account for it. So we have to account for this particular branching also by something called as the branching effort. It's relatively simple. For every time there is a branching like this, we have to calculate for this particular point a branching effort, which is given by this equation. C on path plus C off path divided by C on path. So it looks complicated, but it's very simple. It just means that the total capacitance in this particular output, that is, we have 1, 2. So in this case, C on path is 90, C off path is also 90. So 90 plus 90 divided by 90. So 180 divided by 90, or B equal to 2. If you have one more, then that will come as one more term in the off path capacitance. So we have to add all the off path and on path capacitances divided by the on path capacitance. That will give us a number B, which is called as the branching effort. So this we have to do every time there is a branching. If there are two branching, then you will get B1, B2. If there's three branches in the path, then you get B1, B2, B3, and so on. So if we calculate this branching effort similar to before, the capital B is nothing but the product of all the individual BIs, B1, B2, B3, how much ever. And this is your new equation for effort, G into B into H, and this is what you have to use every time, not just GH. If there is a branching, then we have to calculate B also. In the previous example there was no branching, so capital B was 1. There is no need to put that in the equation, but whenever you have a branch like this, if you don't use it, it will give you a error. You will not get the correct answer. You have to account for this branching also by what is called as branching effort, capital B. Okay, and now your F is G into B into H, and we have to do F to power 1 by N and so on, just like before. Okay, so let us see if we can look at one example with a branching. Okay, very good. So we have one example here. Okay, we have a logic block, and the blue line is our path where we want to minimize the delay, and some numbers are there just like before. So we will try to calculate x and y for this particular case. So we'll go back to our whiteboard. Okay, so first, what is the equation to write? F equal to G B H. Okay, so start with capital G, go back to the circuit. This is my path. Okay, what are the gates in my path? A 2 input NAND gate, 3 input NAND gate, 2 input NOR gate. So we can calculate capital G as G1, G2, G3 equal to 2 input NAND gate 4 by 3, 3 input NAND gate 5 by 3 and 5 by 3. This is capital G. H equal to output capacitance divided by input capacitance. So that also we can write 45 by 8. Now B equal to, now in this circuit, as you are going from input to output, how many places do you have the branching? So this is one branch, B1 we have to calculate. This is another branch, we have to calculate B2, and there is no more branch. So capital B is B1 into B2. Okay, B1 equal to C on path plus C off path divided by C on path. This is my path. What is the total on path capacitance? X. X plus what is the total off path capacitance? X. X. So that is 2x, and the whole thing divided by C on path is x. So this is equal to 3. And similarly B2 equal to, we have on path is y, off path is y, so y plus y divided by y equal to 2. Therefore B equal to 3 into 2 equal to 6. F equal to G into B into H, which is equal to 27. This is capital G multiplied by 45 by 8 multiplied by 6 equal to, excuse me, 125. So therefore okay, now this statement same as before, stage effort GIHI has to be set as capital F to power. Okay, now don't simply count the number of gates, it is the number of stages. This is one logic stage, these three gates are operating in parallel, so this is another logic stage, this is another logic stage, so n is 3. Okay, and that's simple, it's just 5. So if we set this for each stage, then our delay is going to be minimum. So now that we have this, let us try to get the sizes for each gate. Let's clear this. Okay, so we'll start with the last gate if you want this time. So now we have 45 here. Okay, and G3H3 equal to 5. G3 is 5 by 3 into, now we have to be little careful, output capacitance is 45 divided by, what is the input capacitance, is Y. Okay, equal to 5. Therefore y equal to, we solve for 50. Okay, now the next stage, we'll go one stage backwards, we are at the second stage now, and this time also G2 H2 equal to 5. which means that G2 3 input NAND gate, so 5 by 3 into, now at this gate output capacitance divided by input capacitance. Here you have to be a little bit careful. The output capacitance is not just Y, okay, it is giving the output to Y and Y. So the output capacitance for this particular gate is 2Y and the input capacitance is X, okay. So that is going to be 30 divided by X, which means X equal to, you can solve for X, which will give us be 10. Okay, and finally G3H3 equal to 5, which means that first is a 2 input NAND gate, 4 by 3 into, again the same issue, output capacitance for this gate is 3 times X, okay, so that is also 30 divided by, this is a check. As I said the last time also, we cannot calculate this, we can only check it, is it equal to 5. So if you see from this equation, 4 by 3 into 30 by 8 is indeed equal to 5, okay, and that means that all our sizes are correct, X and Y whatever we have got. And now we can also calculate the delay equal to 3 stages, so 3 into 5 plus 2 plus 3 plus 2 equal to 5 3s are 15, 15 plus 7, 22 tau. This is the delay for this particular path, okay, and this is the best possible delay. We don't have to worry about any other combination for X and Y. So stop here for a second, and one last part we will do that in the next video.